Okay, so here we are, note number 6.2, called Average Speed as a Rate of Change. And essentially today's note is about graphs, and it's always the same kind of graphs, and we've talked about this kind before, the distance time graphs. So we're specifically talking about distance time graphs, and we're going to use a special formula, which is rise over run, and we'll see what that means very soon. So let's first look at this example. I know this Charlie here, he looks confused. I think it's because the writing's so hazy. And I'm hoping on your piece of paper on your handout that it's not nearly this hazy. But hopefully just read off the handout instead of off this. But Ferd travels from Stratford to Ottawa and checked his progress. And so here's the table of values. And remember that this will be the x. Time in a distance time graph is always the x, and distance is the y. So kilometers from Stratford is here. So when he starts out at time 0, he's in Stratford. 1 hour later, he's 95 kilometers away. 2 hours later, he's 190, etc., etc. So this is all distance from Stratford. First, it says graph the data. So let's do that. I went ahead and did it actually. I've got the answer down here, so you wouldn't have to wait for me. So first of all, the axes you want to put on, I went up by hundreds, which is okay. It wasn't a bad choice, and I went up by 1, 2, 3, 4, 5, 6 hours on the x-axis, and distance in kilometers, going up by hundreds. The problem with my choice of units, or of divisions, is that it doesn't, my points don't land perfectly, on the grids. So, but you can see what I've done here is I've graphed the data best I could, and I've got a straight line. So my data doesn't look perfect on my straight line here, and that's only because I was estimating. If you look at it and you practice doing grids, so for example, it's at 95, the first point here, I have 0, 0 to start, and then I have 1, 95. Well, coming down here, I've got 1, and there's 95. If you need to pause the tape, by the way, just to get this graph driven, why don't you why don't you go ahead and do that, and then join me. You can pause it right here, draw the graph, and then we'll discuss the graph. I'm going to assume that you've got this all written down, and I've got this bit here, which you might not know what I mean. So once you get the graph drawn, the question again is it linear? Well, my answer is yes, based on just looking straight at the graph. It's a straight line. So yes, because it's a straight line, but I could also find that a different way. And first of all, I'm going to say, let's check off. Make sure when you look at a question, you make sure you answer all the parts. So is graph the data, done. Is it linear? The answer is yes, because it's a straight line. I could also just verify that one other way, and that's using first differences, right? So we could put a little column here, call it first differences, right? And then go, the first difference between there is 95 minus 0, which is 95. The first difference here would be 190 minus 95, which equals 95. And I'll do one more just to prove it, so it's the same so far, right? 285 minus 190. I just know it's a straight line, but it's 95. So I verified that it's linear using two methods. One is the straight line graph. The second is by my first differences. So definitely, by more than one strategy, definitely linear. Okay? Now, find his average speed. Here's the whole thing that's new today, right? Everything else isn't new. You've graphed before, you've done first differences. And here's the new equation. Speed has an equation, and that equation is rise over run. Okay? And, I say rise over run because and that's a divide, right? So whatever the rise is divided by the run. Well, what is rise? Rise is how much the graph goes up or down. If it goes down, it's a negative number. In this case, it's going up, right? The graph starts here and it moves this way. It's going up. And the run is how much the graph goes sideways. So it's the horizontal. So looking at this graph, and how you do that, by the way, the rise doesn't have to be, from the very first point to the very last point, but you could pick any 2 points and calculate the rise and run, but we're going to pick the very first and the very last point of data given. Okay, so my rise, it goes up to, this is 500, 550, It's 570, I know that from here, right? So it's hard to read it off the graph, but the rise is 570. Okay. Oopsie. My rise is 570, and my run is how much it moves horizontally, which is 6, right? I start at 0 and at 6 hours, so the run is 6. So again, finding rise is just how much the graph moves up or down between any 2 points. I'm choosing the first and last points, but the reality is if I chose this point and this point, I would get the same speed because it's a straight line. But for us, we'll just go, first and last point. Okay? And our run is 6. So then when I calculate speed, all I do is say, well, I know it's rise over run. My rise is 570. And my run is 6. So put that in your calculator, 570 divided by 6. I won't do that in my head. $95. Oh, I should have done that in my head because I should have known it because it's the first differences, coincidentally. Okay? And the units, by the way, speed isn't just 95, right? What is we measure speed in? It's kilometers per hour. We measure speed in kilometers per hour. Okay? Now, you could have figured that out right away because of our first differences being 95. And also, I just look at the first 2 data points, assuming that the speed doesn't change. You say, okay, 1 hour he drove, right? He rode 1 hour, he drove 95 kilometers. 95 kilometers per hour. That's what it means. Okay? So that's the speed. So I didn't need to put that in my calculator. But I found it in this case using rise over run. Again, if you needed more time, just pause the tape, right? Pause the tape and get the writing, get everything down, and then move on to the next. Okay, so speed is equal to what we call rate of change. And by the way, rate of change, sometimes we call it rock. And we're going to use that term fairly frequently, rock. Okay, but speed is rate of change on a distance time graph. And it's also, the equation for it is rise over run. Units are whatever's basically given in the question. So it's what's on the y-axis per unit on the x-axis. So what do I mean by that? Looking back at the last example, right? The y-axis was kilometers per hour. So it's whatever's on the y per whatever's on the x. Distance over time. Okay? So let's do it for this example right here. We want to determine each rate of change, which is speed. Okay, so those get used back and forth. Now this is very hazy, but that says distance in meters and time in seconds, which by the way tells me that my units are going to be meters per second. I know that now. But I'm going to go through and calculate my rise and my run. Now, hard to read, but it does give us some data points. He starts at, if I use these 2, remember I said you don't have to use the very beginning and very end. You could use any 2 points, and I'm just going to choose to start here and finish here. And in that time, the rise went from 2 up to 8. So my rise is 6. Right? Between those 2 points, it went up by 6. And my run between this point and this point, right, went from 1 second to 4 seconds. So my horizontal distance is 3. Right? 1 to 4 is 3 from here to here. So that means my speed is 6 over 3, which is 2. And you always have to include units. So it's meters per second. Okay, another example. This one is very interesting. This one, my rise, right? I start here at, that should be a 4, hard to see. And I end at 1. So my rise is not 3 because it's going down, right? It's got to be -3, right? So it dropped 1, 2, 3. That's how much I dropped. 1, 2, 3. And my run, it went across, that's 10, right? So 10, 20, 30, 40, 50, 60. My run is 60. Okay? So I can't even read what that distance from home. Let's say kilometers. 3. Yeah, that's all right. So his speed is negative 3 per 60, which is a really small number. But you can just divide that. Put that in your calculator. I'd never do that one in my head. Go ahead and put that in your calculator. And 3 divided by 60, 0.05. And it's okay to get a weird number like that if that is what it is. And it's negative. And the units must be, I'm reading that to be kilometers. I hope I'm not reading it wrong. Kilometers per minute. Okay? So negative, it's okay. It can be a negative. Take physics and I'll explain to you why it's okay to be negative. Last one here. This one has no data points written on it, but you still use the same idea, and it's really not that difficult. The run this time is hours, and we have, what, kilometers here. So it starts at 0. It goes as far as to here, which is 3, right? Starts at 0, ends at 3, so it goes 3 hours. That's my run. And my rise starts at 100, ends at, what's this, ends right here. Right? So it's going up by 100, so that must be 250. Right? Starts there, goes up to there, so it goes up 100, 150. So the rise is 150, right? So remember, the rise isn't 250 because it starts at 100, right? So the rise is from here to here. That's how much it changes. So it's 150. So my speed equals 150 over 3. That one I can do in my head. That's 50. And it's kilometers per hour. Okay? All right, time to work on your assignment. So I want you to work away on your assignment, and you will be done when you see 6.3. When you get to 6.3, you can stop, and that'll be all you need to do for now.